In this video, we'll discuss validation, an approach to measuring model quality. Let's start with some motivation. Suppose we want to build a model of y by predictor x. Let's start with a simple one predictor model. Though this looks pretty good, maybe we can do even better by using two predictors. Specifically, let's incorporate the quadratic term x squared as a second predictor. And maybe I'm imagining it, but this does appear a little better than the one predictor model, which is exciting. But maybe we can do even better by using even more predictors. The model shown here uses 9 predictors of y: x, x squared, x cubed, all the way up to x to the 9th power. And it perfectly captures the behavior in y. All of the data points fall directly on the model. There are 0 residuals or 0 prediction errors. But something seems a little off. Though this model perfectly models our sample data, how accurately would it predict the y outcomes of new data points? Let's try it. In the bottom row, the red points represent 10 new data points and the blue curve represents the one predictor model that we built using the original data. That is, this blue model here is the same as the one above. And this original model does okay at describing the new data. The two predictor model seems to do a bit better at describing the new data. And the 9 predictor model, well, is a bit terrible and silly. This model was clearly overfit to our original sample data and is not an accurate representation of the relationship between y and x in the new data points. In general, when we add more and more and more predictors into a model, it can become overfit to the noise in our sample data. In turn, the model loses the bigger picture and does not generalize to new data outside our sample. That is, it results in bad predictions. To prevent overfitting, we can utilize model evaluation techniques that don't just ask, how well does our model predict the outcomes of our sample data, but how accurately does it predict the outcomes of new data points? In practice, though, we only have one data set. So in order to understand how a model built using this data performs on new data, we can do something clever. We can randomly partition our data into 2 pieces, which we'll call the training set and test set. A common choice is to use an 80%, 20% split. That is, put 80% of our data points into the training set and the other 20% into the test set. The process of using the training and test sets to evaluate our model is called validation. First, the 80% of our data that goes into the training set will be used to train or build a model. The in-sample or training mean absolute error, or MAE, provides a measure of how well this model predicts the outcomes of the training data. Here, the predictions of the y outcomes in the training data, calculated from the training model, tend to be off by 5 units. However, what we really want to understand is how accurately our model can predict the outcome of new cases, and this is where the test set comes in. We can now use the training model, represented by the blue curve, so the blue curve is the same in both plots here, and we can use this training model to predict the y outcomes of the test data. The resulting predictions tend to be off by 5.5 units. We call this our test MAE. This metric provides a more honest measure of how accurately our model can predict the outcomes of new data points, not just the data points that we use to build the model. And, as is often the case in practice, the test MAE here is slightly bigger than the training MAE. Naturally, the training model performed better on the training data. To conclude, let's consider some potential pitfalls of this validation method. First, this method only utilized 80% of the available data to build a model. But the less data we use, the worse our model estimate will be, on average. In turn, we might actually overestimate the true error of the model built using our full dataset. Consider a second drawback. Since the data is randomly assigned to either the training or test set, it's possible to get a bad split. For example, in the extreme example shown here, all of the cases with larger x values were randomly assigned to the test set. In this unlucky event, the test cases exhibit a positive trend, whereas the training cases exhibit a negative trend. Thus, the training model would perform poorly on the test cases, resulting in a large test error, which likely overestimates the true model error. In the sequel to this video, we'll learn a clever approach to avoid these pitfalls.